And this lecture will be given by Professor António Pascoal. He's a professor in controls and marine robotics from Institute of Systems and Robotics from Instituto Superior Técnico. He has more than 30 years of research experience and teaching and research experience. He is very well known in this field. He's coordinated and participated in a large number of international projects that have led to the design and development and field testing of single and multiple autonomous marine and air vehicles. He has a close relationship with NIO, National Institute of Oceanography, Goa, and many other postgraduate schools in USA, Korea, and Europe. He is a PI, principal investigator to many of the European Union funded projects, very prestigious projects, which is for exploring the sea, for the survey, for the surveillance. And he has been, he has a lot of his eminent personality and experience in this field. He has participated in many European Union projects like VMUST, MORPH, CADI, CO3 UVs. So about which he'll try to put a little bit of glimpse on these projects. And moreover, he's a very friendly and humble personality. It is so.
Thank you.
We are very happy to have you here, sir. And I hope this will be a good platform for you to learn. Now I will hand over to Professor António to start the course. Thank you, sir.
So can you hear my mic? Okay, good afternoon. Thank you very much for coming. It's a pleasure to be here again and visit IIT Madras at the invitation of Professor Suresh under the Sparc program. Now, the task is not easy because I know you guys are in ocean engineering, but probably you have not heard much yet about all types of marine robots and how is it that we build them and we make them operate at sea. So this very first part, it's an introduction. Maybe I should have cut it a little bit, but I'm always concerned that there may be students that don't have a very clear idea of what's going on. So I think it's very important to motivate. I know what the situation is in Europe. I don't know if it is the same in India. If you apply for funding, for example, from the European Union, and you propose some, outrageous subject, they will come to you and ask you, what is this for? How can you justify the funds? And I think it's also true because I think the most exciting problems are strongly motivated by what happens in real life. What problems is it that we have to solve? So I hope that in the course of this first introduction, I will explain to you why is it that we have to develop these robots and then guide you through the different steps involved in the design and operation of these robots. And then we'll stop a little bit and we'll get into more technical stuff, but I will not go very deep into this subject. So I'll touch upon modeling, control, navigation, and then a topic that is quite fancy these days that has to do with cooperative systems, multiple systems operating at sea. There's a lot of stuff being done with air vehicles, but also with marine vehicles. As you'll see, it's very exciting. Now, I like to stand while I give the lecture, but okay, I'm not used to this green stuff, so I'll sit because I have to look at the screen, okay? So let's move fast because there's a lot of things that I would like to show to you. So admit, okay, I have admitted a person. Okay, so I come from the University of Lisbon in Portugal. Oh, that, yeah. Okay, sorry, no problem. Okay. So this is the largest school of engineering in Portugal. It has two campi, one in Lisbon and the other one close to the river. And as you can see, we have dual doctoral programs. Actually, we have students that get their degrees both from IST, that's the name of the institution, and EPFL or Carnegie Mellon, and also the MIT. And we open calls each year to award these double degrees. So the work that I'm going to describe has been the work of many people. This is just a sample. And you see some of the robots that we have constructed in-house. I also like to show these next slides. I mean, they don't mean much by themselves, but if you pay attention, this is an example of a European project called GREX, and see the amount of people involved. That's what excites me about these projects, because you have people from different countries that have to work together. In this case, there were 5 countries, from Germany, France, Portugal, so on and so forth. So this creates many problems because people come with different vehicles, with different robots, and then we have to sort of develop some kind of interface so that they speak the same language and do wonderful things at sea. This is another example of an even bigger project called CO3 AUVs. I'll get into this. I'll describe to you what we were doing here. And you see, it's a very large group of people again. This was the final demo in 2012. It was almost 10 years back. And again, you see some of the vehicles that were used. Another example that I will focus upon is the Morph project. Again, large groups of people. Here you see more vehicles. You see on the left surface vehicles, and in the front our underwater vehicles, and on the right the vehicles that are being developed in Spain. And this is one of the most recent projects called We Must. Terribly challenging. I'll mention to you what is it that we did under this project. And as you can see, there were many people performing these final trials. I think it's important for us engineers to learn how to work with other people, so we cannot live in isolation. Makes things difficult because we have to interact with people. They are in different countries, so we have to use the internet, we have meetings, but still it's a bit difficult, but also very challenging and rewarding. So in order to do this, we have to use robotic vehicles. And here are some examples of vehicles that we ourselves developed at IST Portugal. And you can see, it's not going to ring. Oh, interfere. Okay, sorry. So you see examples here. You see on top, you see autonomous surface vehicles, which you have here at IIT Madras. So they have strange names because they mean something in Portuguese. Delphin is the youngest son of the king. Delphin X. Then at the bottom, you see one of the first AUVs that we developed called Infante. And then we developed the vehicles that are in the middle section called Medusa, that we are very proud of, okay? So the big question is why, I mean, I'm sure you know, some of you know in very clear terms, why is it that we need robots for ocean exploration? But let's get into this. So first of all, there are fundamental scientific challenges and also commercial challenges. So why is it that we need marine robots to meet these challenges? And I'm going to focus a little bit on the theory and practice from single to multiple robotic vehicles, an overview. So what are the scientific challenges? And these apply no matter where you are, United States, in Africa, here in India, you go east, China, Russia, everyone is concerned about this, to study the ocean. So to study all kinds of phenomena that occur in the ocean. And most importantly, this is probably the most difficult part, to know the interface between the ocean and the sea bottom, and also to know the interior of the earth, and also the interface between the water and the surface. I'll give you an example. I mean, you may shrug your shoulders and say, why do I need to know about the interior of the earth? I have a very good friend of mine that was the chief scientist for a big expedition in Papua New Guinea. And they had a fantastic ship, and they drilled. I mean, the water column was about 2 kilometers, and then they drilled about 1 kilometer. And when they extracted the core, they verified that there were lots of bacteria living there, God knows how. And it's estimated, this is called the Deep Biosphere, and it's estimated that the Deep Biosphere far exceeds the biosphere that we are used to thinking of in air, on land, and at sea. So it's very important to penetrate. Of course, it's difficult to do that with robots, or impossible. It's important. Now, in order to study the ocean, we need advanced technology. And more we are making use of what we call cooperative robots, more than one robot, and I'll explain to you why. So the acronyms there, you see, you have all kinds of vehicles that I'll mention to you. AUVs, this stands for Autonomous Underwater Vehicle. So it's a vehicle that goes about its life and doesn't have an umbilical cord. Autonomous surface craft, these are ships that are autonomous. And then you have other kinds of vessels and vehicles as well. I don't know if I'm the one that should, probably I have to give them permission, right? Yeah, 1, 2. Okay. It should go away. Okay, right there. So I'll give you an example. This is the reason why I became so much interested in ocean robotics. So you see a map here. You have Portugal, Spain, North Africa, and then you go down. You have the United States and Brazil on the other side. And you have something fantastic that is called the Mid-Atlantic Ridge. And right there in a region that is Portuguese called the Azores, it's a meeting point of 3 tectonic plates where they are spreading over the years. So, it's actually the Earth crust is separating here. So that's what we call a ridge, a Mid-Atlantic Ridge. Now, why is the Mid-Atlantic Ridge important? So let's see here. So again, it's the point where the tectonic plates meet. If you look on the right, these are very interesting, let's call them photographs. They're water obtained from onboard ships, but of course they could not use vision, they use acoustics. So how are these maps obtained? So suppose I want to get the map of this room over here, and I have something that emits sound. So emit the sound, wait for the reply, measure the round trip travel time, divide by 2, divide by the velocity of speed of the sound in air, and you get the distance where it touched the wall. Then you keep doing and you do a cross section. And then you go to higher height. So eventually you are going to have sort of a nice map of the area. That's how these things are obtained from the surface, and see that they are mapping things at 2,300 meters, 1,700, so on and so forth. This is something that you have to bear in mind. Underwater, most of the time you see with your ears because the visibility is not there and you need high power sources, right? And also you have these fantastic things called the deep water vents, and the deep water vents are very important because I'm sure you have seen these things that you call the black smokers. So at the bottom of the earth, when you have this Mid-Atlantic Ridge, you have water that emerges from the inner Earth's crust, and then you can see all minerals because the pressure is so high, they do not dissolve, and that's what you see there. Now, why is this important? Because you have strange forms of life there. And many of them were only discovered in around 1974. And you have something called extreme life forms. Now, people are already mapping the genetic material of these bacteria and use the material for genetic purposes, because they essentially live in a very corrosive environment. So they know how to repair themselves from a genetic standpoint. So for the pharmaceutical industry, it's very, very, very important to study what's going on. So there's a large potential for the biotechnological industry, exploration of mineral deposits, and there's a lot of this in India, okay? Of course, there's the problem there, because if you start scavenging the bottom of the ocean, then it will destroy the habitat environment, so there must be some form of trade-off there. And probably the other window on the evolution of life. So it's very important to study these deep water hydrothermal vents. This is an example of how engineering can come into play when it comes to mapping these hydrothermal vents. Because people are so very much interested in the biological activity, these maps were not obtained by us. They are obtained by our friends from the Woodsole Oceanographic Institution, a very prestigious university or institution near Boston, near the MIT. And see what they did, they wanted to map one of these, let's call them chimneys. So they sent a vehicle with an umbilical connected to the ship, and they were doing very fine maneuvers around the chimney, sending the acoustic waves, as I mentioned to you. And then at the end of the day, you could recover the 3D. And then using cameras very close, they could have a map of the types of bacteria and shrimps and clams that grow into these areas. So you need technology to do this. It's very important to get these maps. All right, this is an example of a scan that we did with one of our instruments. We were on board one of these vehicles, and you see the scan. We are scanning, so you get a cut of the chimney. So this is very important for scientific applications, because you get to have a map of the area, and then if you can map also the biological stuff that lives in there, it's very important to study it over time. In order to study the deep water hydrothermal vents, how do people do that? You can use manned submersibles. This is a very famous one. It's called an Nautil. It's French. It was developed by the famous French institute called Ifremer. So there are people on board. They go inside the titanium sphere that is somehow at the bow. These things are very costly, and they put lives in jeopardy, okay? So in situ observations. Now, these vents in general are very, very hard to study for a number of reasons. Large depth. I mean, if you go to 3,000, 4,000 meters, and you are building a machine to go that deep, you have to worry about the pressure containers, and can they withstand the pressures or not. You have to be very, very careful. Highly corrosive. And then, of course, you don't have or virtual no optical visibility, so are essentially blind, unless you carry, you know, strong lights and good cameras. And this is one of the most challenging things in underwater robotics, to find out where you are. Where am I? You don't have GPS, so what do I do? This is probably one of the most difficult problems, more than controls. Navigation is extremely hard. Okay. Here are some examples of these vents. And here it's not allowing me to touch it. Oh, it should be there. I don't know. It's named on. And here you see a remotely operated vehicle with some form of device sucking these shrimps to study back in the labs. You see all kinds of interesting things that grow there. Okay, so let's move on. I'm going to show you something interesting that was given to me by these people at the Woodsole. It's the first time that a magma explosion was captured underwater. So I'm going to skip this. They were not using an autonomous vehicle. They were using an ROV, which means a vehicle with an umbilical, but the pilot just saw this magma explosion underwater. So that's another beautiful use of these techniques. Okay. So the Azores are really interesting. There are many, many interesting regions here in India. So it's a small surface terrestrial area, and there are many islands. And then there's a special island here. It has a name, doesn't matter. And then it has a deep water volcano there, not a shallow water volcano there. Here, the pressure is not so high, so the minerals dissolve, so it's very clear, but you still see the bubbles coming out of the interior of the Earth. So you see other kind of hydrothermal vents. These are shallow hydrothermal vents, you see. And then they leave all kinds of deposits of bacteria, minerals, and other things. And it's very important to study them. Now, typically, how is this done? You have divers that go there, but this is very, very, very primitive to find out what's going on in this environment. It would be nice to have an automatic way of finding this hydrothermal activity and then to go there and study in situ. Okay, so let me. So what means do we have available to study the ocean? Of course, you have oceanographic surveying where you have ships, okay? And these will always be there, except they are extremely costly, very costly. And then there's another problem. Suppose you want to map a certain area, 100 kilometers by 100 kilometers. And you want to study how the temperature, salinity, and other stuff are evolving. You cannot do this with a boat or a ship that starts from here and goes back and forth, because by the time it will get there, let's say after a month, there's no way you can get a snapshot of the map of temperature and salinity and whatever. So you should resort to autonomous robots, have many of them doing this survey. This calls for the use of multiple vehicles, which is a very interesting and important application. Okay, let's move on. So also, please bear in mind that we are in a school of engineering. I also come from a school of engineering, but more and more, we need to be related to commercial activities and society at large. So all that we can do is to afford the scientists instruments and methodologies to acquire data at the appropriate scales. And then we should help them do the signal processing and data fusion to perform management, dissemination of information. And then whoever is responsible should make decisions and, okay, we have to go back there and acquire more data. And this is very good for the preservation of marine habitats. So there's a very important issue because you know from Nyquist's theorem of sampling, if you want to capture what is in a signal, you have to sample at least at twice the highest frequency. So if you want to sample a large volume of the ocean, and there's a spatial scale and a temporal scale, they dictate how many points you should take and how often, the periodicity. And most of the times, this is not done because of the lack of means available. So it's very important to develop robots that can do this job. So I talked to you about applications in coastal, open sea, and deep ocean. The classical methods, of course, are the divers. And here is an example of a friend of mine that is sort of looking around, riding a scooter and carrying something called a side scan sonar. I'll mention to you what this is, but he will not go very far because even if he acquires good data, the question is, where did I acquire the data? That's what we call georeferencing the data. And this is an important quality of robots. When you acquire the data, you should have the temporal and spatial tags attached. And this is a difficult problem, okay? Okay. So this is, of course, dangerous, a little bit. Oh, sorry, it came back. So then you have the classical methods, the semi-classical methods. That's when you start penetrating the water column. Then you have humans on board. And people have been developing this. I mean, the Russians have many. I know that India was building one here at the NIOT. The Chinese have, the US has many, so on and so forth. They are very expensive. And again, they place human lives at risk. Sometimes this doesn't go. Okay. Now, you have probably read these fantastic books of Jules Verne, and there's one called, it's called something, So Many Leagues Under the Sea, right? You have seen that. This title is in French. But when he conceived of these contraptions, he already devised all the basic systems that go into the making of some platform that could carry humans and observe the ocean. And one of the very interesting things is that, so here you go, all right? So here Captain Nemo is actually doing the navigation by resurfacing and finding out where he is. Things started shaping up before people decided to go to the Titanic, but it's here that it got into, people became passionate about these things. So the Titanic, you remember, and then the first time, one of the first times they inspected the Titanic, they were using Robin, a very small robot. This is a typical example of what we call a remotely operated vehicle. So it's a vehicle that operates underwater and has an umbilical. The umbilical must be connected to a manned submersible. So there was a manned submersible, there was the umbilical. Now, this is very, very different from an autonomous robot, because here the operator is sending commands to the robot and watching what the robot is doing. So actually it's commanding every motor at the time. So it's not automatic, it's not autonomous at all, but still very interesting. So operations with an umbilical. So bear in mind, this is what we call a remotely operated vehicle. So the manned submersible was the Alvin, and there you see the little Robin going inside the Titanic, and they got wonderful shots, okay? So modern things along these lines. So there's a bunch of ROVs in the market. God, there are so many. As far as I know, there's a company here in Chennai that manufactures ROVs. So what's the problem here? Most of these ROVs are commanded through an umbilical, so it's very tiring for the operator. So the question is, can we make it almost automatic? So instead of commanding each thruster in separation in order to move forward or sideways or up and down and rotate, you should be able to give high-level commands. Go forward at a certain speed, and the vehicle should recruit the thruster activity to do that. Go sideways, rotate to a certain angle, and it should be done automatically. So it's possible to do that now. Okay, now what's the problem with these ROVs? So here is an example of an ROV that we operated in the Azores. It's near one of these old volcanoes. The currents are very intense. You see the umbilical is almost stretched. This means at some point you don't have any control authority. The drag is huge and you don't have enough power on your actuators to counteract. So the dream would be to cut the umbilical, cut the umbilical. The moment you cut the umbilical, you have two problems, because you have to have the energy on board, because here the energy is on board the ship. And the second one is all the intelligence should be on board the robot itself. So you get into what we call autonomous underwater vehicles that they don't have any umbilical. Okay. So there are many examples of autonomous vehicles. The one on top on the left is especially interesting because it was developed by NOC. Now I think, no, it used to be SOC, Southampton Oceanography Center. Now it's National Oceanography Center in the UK. It was a fantastic vehicle, and it's somewhere under the ice in the Antarctica. So they were studying the populations of krill, you know, these microscopic shrimp. So they programmed the vehicle to go under the ice and being able, you know, being very smart, recognizing the layer of ice above and then the bottom, and navigate. It got stuck, and they have no idea why. So it's there. I think it was about 2 million euros, which, well, it's equivalent to dollars now, $2 million. Now, don't get discouraged, because more and more we can build robots that are very, very good, and they are not that expensive. Okay, and then in the class of autonomous vehicles, we also have a very interesting class that only very recently came to the fore. I don't know why. They didn't used to be very popular. They are called the autonomous surface craft. These are vehicles that operate at the surface, and you guys have some here. There's another kind of vehicles, because if you look at most of the AUVs now, that is changing. They used to be designed to keep moving, you know, torpedo shape. But if you want to interact with the environment, like, for example, if you want to do the maintenance of infrastructures underwater, you need to equip these vehicles with manipulators to go and manipulate whatever is there. These are called intervention autonomous underwater vehicles. And this is a very, very important class of vehicles. People are starting to imagine these kinds of vehicles in operation to do the inspection of offshore infrastructures for energy harvesting, so wind energy, wave energy, and also for aquaculture, because you have these big farms and you need to inspect them. So why not develop these vehicles to go there and maneuver in these complex environments and possibly turn some valves and stuff like that and come back up? So this is a big challenge. There are only a few worldwide. I mean, as far as I know, there was one in Hawaii, but they are no longer doing research. This one is a French one. There's a Spanish one. There's a Korean one, and I'm not aware of any other vehicle of this type. So a vehicle equipped with manipulators. Okay. So there we go. Oh, all right. There's another beautiful kind of vehicle that is called the glider. Maybe some of you have not heard of this. NIOT, I think it's operating 2 gliders here in the ocean on East. So I'm sure you are used to the word gliders in air. So essentially they have these big wings. So even at low speed, they have the lift required to keep them maneuvering and flying. This is the same, but underwater. So the question is, why do we do this underwater? Because if you want to leave a vehicle at sea for extended periods of time, months, we are talking about months, you don't want this vehicle to waste too much energy. So what you do is something beautiful. You have the vehicle at the surface. Now, you start, there are many ways of doing this. So you could design the vehicle to start coming down. The vehicle is heavy. And then because it has the wings, it will fly down, okay? So when it gets to a desired depth, then you inflate the bladder with oil. And the vehicle becomes buoyant and comes to the top. So there's this, what people call the yo-yo motion. And in the process, they acquire data for large sectors of the ocean, and then they transmit via GPS. There are fantastic problems to be solved here. Navigation is not solved. It's crude navigation. Most of these vehicles do a very simple navigation, and they try to correct when they come to the surface using GPS. So there are ways of improving this. That's an example of the data. The other thing that I wanted to impress upon you is that underwater you see mostly with your ears. What you see here is some data that we have acquired in the Azores using what we call a multi-beam. So instead of sending a single ray, acoustic ray, you have a vehicle going and it sonifies a certain area and then electronically listens to the replies over very small angles in succession. And then by collecting the data and plotting it, this is the bottom of the ocean. Of course, the colors are artificial, but this is an example of one of the units that people use to do scientific and commercial surveys. Here you can see very well the bottom of the ocean with so much detail, okay? Now, what are the future trends? Networks. More and more you need more than one vehicle cooperating to perform a job, because you want to perform your missions faster. You have to have more reliable vehicles so that even if one of them is lost, okay, you still have a bunch of them to do the job. And because there are other missions where you actually need to cooperate, you need cooperation among vehicles. There are many examples of sampling networks, some initiatives in the US and the Coriolis initiative. These are by now classical. I'll mention something much more interesting to you later in the talk. Okay. I myself became interested in what we call cooperative control and cooperative missions around 2000. For some reason at IST, we're pioneers in this concept. Then, of course, we brought many European partners into the picture, and the idea is very simple. Suppose you have an underwater vehicle performing a mission. Okay, you tell the vehicle, go to a certain altitude above the seabed, keep it, acquire images with a camera, with multi-beam, and then come back to the surface. Now, immediately the scientists told us, no, that's not the way we operate. We like to know more or less what is going on. So if you want to know more or less what's going on, you need to communicate the data, not in real time, of course, but now and then. This is a very, very difficult task. So here is the scenario where you have an autonomous underwater vehicle, an autonomous surface vehicle, and this guy goes about its life taking images of the ocean and sending them to the vehicle, and the vehicle could then command the mission or change the mission according to the data that is acquired. What's the problem? The problem is when you are underwater and try to communicate with the boat, you use acoustics, okay? So you send an acoustic ray, but of course, it's not a single beam or a thin beam. It has a certain width. So you are going to go up and down and up and down and down. This is what people call multipath. And so the receiver, the human on board, it's quite confused. It's very hard to try and understand what is being communicated. Of course, there are ways of doing this. People that work in communications know how to do this, but it needs computational time, and the baud rate, the rate of transmission goes really low. Things would be extremely easy if you could operate these vehicles in such a way that one would stay always on top of another one, because now you don't have the multipath, you have the direct ray. That's it. That's the basic idea behind this project. So the idea was to transmit in the vertical. So we came up with the concept of developing an AUV, which we did, an autonomous surface craft, which we did, and then programming this guy here to do a certain mission, and then this one would automatically stay on top and receive the information from the bottom one. This can also solve a very important problem, because when the underwater vehicle is going about its business, it should know where it is. That is a very difficult problem, which is trivial for the surface vehicle because it has GPS. So of course, this guy can send via an acoustic modem. Those are available. Its inertial position, but still you should be able to measure the relative position of this one with respect to the top one. And it's only very, very, very recently that units capable of doing this, that are light, compact, and cheap, came into the market. They are called ultra-short baseline systems. So the combination of acoustic modems, ultra-short baseline systems, good control systems, now you have all the tools to go into the ocean and start doing something exciting, all right? So that's what was happening around 2000. We didn't have those units, so we're not extremely or completely successful in achieving what we had promised, but those were very promising steps. So here you see the two working in a tandem, working in a cooperation. Okay. There are other reasons why people would like to use cooperative systems. For example, there are, I showed to you the existence of these deep water vents. They are called hydrothermal vents. They are very important for the reasons I mentioned to you, and for other reasons. So the question is, how do you find them? And the way the guys at the Woods Hole do that, is by using a certain vehicle that does a scanning and tries to sniff for a gas that is emitted by the sources that is called methane. But you can conceive of a fleet of multiple vehicles here. They maneuver information, and by measuring with different vehicles, you can measure the gradient. And then, as you guys know, if you do what we call a gradient ascent, I mean, essentially, if you have a scalar field, how do you get to the top? You follow the gradient. So that's what this picture is. This has not been done yet. Okay, methane plume. One of the first projects where we really accomplished something very, very interesting using multiple vehicles was the MORPH project, where essentially we had to do deep sea habitat mapping near hydrothermal vents in complex 3D environment. What do I mean by this? So scientists they need to build what we call habitat mappings of the bottom of the ocean, not only of the form of the terrain, but of the animals and plants that grow there. Some of the most exciting things happen on the vertical cliffs that, you know, come from the coast, boom, directly into the bottom of the ocean. I don't know why, I'm not a biologist, but I'm told that some of the most exciting stuff happens there. So the question is, how do you send a robot there or robots to map this wall? It's very dangerous to send an ROV based off a ship, because then the ship is very close to coast. And if the activity at the ocean is very intense, then it could smash against the rocks. So, but the end product should be something like this that we do routinely for other types of scenarios, so it is multi-beam images. So how do you obtain habitat marine maps of complex underwater structures? We know how divers do that. They just go there, 1, 2, 3 of them, and they observe, but it's a very coarse approach to habitat mapping. So we came up with the idea of developing what we call a supra vehicle called MORPH that consists of many vehicles working in cooperation, and each one is good at its own thing. So let's see here. Okay. So I'll show you. This is what we actually built in practice. So suppose you want to map the seafloor, and now suddenly you encounter like this wall, and you'd like for these guys to do a transition where you go from mapping the ocean floor to start mapping the wall, going sideways, coming back, going sideways, so on and so forth. So this is the way we did it. We developed 5 vehicles. The top vehicle knows exactly where it is using GPS. Then there's an intermediate vehicle here that is in connection with that one acoustically and is capable of finding out where it is with respect to that one. The same applies to this one with respect to this one. This one is the most intelligent vehicle because it carries this multi-beam to detect the onset of the wall. So upon detecting the wall, it tells the other guys, hey guys, we should now start tilting our plane of operation, and go along. And then there are a couple of vehicles here. There are only 2, but you could have 3 or 4. That the only thing is they measure the ranges to this vehicle, and by using some appropriate algorithms, they can keep a formation side to side and map the seafloor. So this was a very, very interesting project. No, I don't know. Okay. Again, to give you an idea of the magnitude of the consortium involved, so we had 10 partners, 9, and the Woodsole was there just as a consultant, and we had all kinds of vehicles and experimental facilities, and I'll show you some examples of what we achieved. Now, to give you the general perspective of what's going on in marine robotics. So I mentioned to you that we need more than 1 vehicle in operation. There's this concept that when you design a system, first of all, you have to talk to the end user. That could be a commercial company, a scientific person says, this is what I want to do. I want to acquire data about the ocean. I want to map the ocean floor. I want to inspect the infrastructures. This is what I want to do. These are the user specifications. From the user specifications, you distill what we call the functional specifications. Well, in that case, I should have a machine that is capable of performing autonomously, being able to detect obstacles, obtaining data, so on and so forth. And then the last step is to go from functional to technical. What kind of machines are we exactly talking about? So don't even think of starting developing a machine just because it's cute and it looks good. You have to have an application in mind, all right? Once you get to that point, then you have to instill the intelligence on board these cooperative systems. And the first block is the planning. You have to plan something. Of course, then you can do replanning. So I have this large volume of the ocean. I know more or less how the temperature is distributed. I want to get a good map. I have 5 vehicles. I have so much time to get the data. What am I going to do with them? You have to plan. That's where you plan the trajectories, okay? So now you know what you want to do. You know what you want to do, so you know what routes you want to take. Now you need to know where you are. That's called cooperative navigation. Navigation is robotic. In robotics, is not the act of moving from one place to another. It's the act of finding out where you are. Navigation. So once you know where you wish to go, and once you know where you are, then you bring in the paraphernalia of control and cooperative control. These are the 3 building blocks of any serious multi-robot system: motion planning, navigation, and control. So in the course, I'll cover some of these topics here, okay? For example, when it comes to cooperative path following, cooperative control, here is a very, very simple example. Suppose you wish to have 3 vehicles and you want to go them along parallel lines, you know the lines, because each one of them is equipped with a sensor to look at the seabed, and they may be different sensors. So it's essentially you give a path, and then you establish a vehicle formation. It could be triangular or whatever. You tell the formation to go at a certain speed, and the fleet is supposed to converge to these paths and keep a desired formation pattern. It's one of the most simple examples of cooperative control. Sometimes people call this formation control, all right? So in the literature, sometimes you see people talking about swarms. I don't like to use the word swarms because it's something that I respect very much in nature when you have swarms of 1,000, 2,000 birds and other things. In marine robotics, maybe you have 10, 12. I don't call that a swarm, so I'm very humble about this. Okay, so that's an example. You also have cooperative target tracking, and this is, you can see the immediate use in military applications that I'm not interested in. If you have a target underwater, and you have a vehicle that can sort of sense where the target is and trying to predict its behavior, and then you have a bunch of vehicles equipped with whatever, trying to track that target. It's cooperative target tracking, okay? So that's what you do there. So I'll get into the theory later, but not very deeply. Now, in order to make all these things happen, you have to have access to marine vehicles, and in particular, autonomous vehicles. Nowadays, again, of course, to research in simulation, but to me, it's not very, there's something lacking, and the real problems arise when you go in the water. So you need vehicles. Now, what's the good news? In the past, it used to be extremely expensive to build or purchase these vehicles. That's not the case anymore. You can make fantastic vehicles that are relatively cheap and that you can operate at sea. So, for example, at IST, we manufacture these vehicles called the Medusa. They can either operate at the surface or underwater. And this is the very first time that we did cooperative control of 3 Medusa vehicles. So now what you are going to see, it's a little bit of cheating because they are still at the surface. So this means that they can communicate using Wi-Fi. So I hope we'll be able to do such an experiment here at in Chennai, IIT Madras very soon with at least 2 vehicles. But it was the first time. So for me, it was very exciting. So you'll see a maneuver of cooperative path following here. Okay, let me. Only one of the vehicles knows the speed that we assign to it. The other one should learn on the fly what motions to take in order to stay in line. So for example, here they are going to enter an arc of circumference, and the guy that is on the outside should know automatically that has to go faster. So they are communicating. They are trying to synchronize. People also call this reaching consensus. And tell me, I mean, I tell you, it's a beautiful thing to see when these vehicles, they take a life of their own, okay? Because you can give them extremely complex trajectories and they go about in a coordinated manner. It's very pleasant to see. So hopefully in the not so distant future, we'll have 2 ships doing this form of maneuver and more exciting maneuvers. So that's an example. So this is not important. There are other applications that probably you never dreamed of, and these have to do with the interaction between robots and humans in the loop, which sounds a bit strange. Okay, I'll tell you why I got involved in this. We were doing a survey of an old sunken ship at about 60 meters deep. And there was an international team, including a team of very, very good divers from France. But they never encountered these conditions. It was extremely dark. The currents were very strong, and 2 of them almost died there. So the question was, my God, can't I find a way of guiding those divers so they got lost? I'm sure the Navy has solved this problem, but we don't know much about it. So we started thinking of a project whereby you could have 1 or more vehicles at the surface guiding a diver underwater, doing something exciting. And this was one of the first projects worldwide, I think, in the area. We were not the coordinators. So the idea was, you have a certain area you want to inspect. And you start with a plan. And you give a plan to the diver. Look, I want you to go from this side to that side along a straight line, and along a straight line, straight line, straight line. And the diver goes. And now I should have 1 or more vehicles at the surface help. So here is how we did it. The diver starts going, and then it has a beeper. It emits an acoustic signal on the back. And these guys know when the beeper is coming, when the mission took place, because the clocks are synchronized. So from measuring the ranges and then doing an operation that is called trilateration, they find out where the diver is. And then they know how off the diver is from the path. And then the diver carries goggles. And so they instruct the diver to go left or go right, so that the diver ultimately goes along the path nice and easy. And this worked. This actually worked. It's a very cute project for a master student, by the way. I mean, it's an exciting project. So basically we had the diver segment with a bunch with goggles and the emitting unit on the back. Then you have these vehicles and you have the mission control segment. So I'll skip through this. So it's what we call a diver tracking system based on GPS and range data. And the range sensors, they are very cheap, very cheap. So you see, this is what went on the back of the diver. So of course the goggles, and then an acoustic modem and the microprocessor and an attitude unit, so on and so forth. So here was our forced voluntary to go in the water with the goggles. Here we go. the system's initialization. And this was the first successful mission where you see the 3 vehicles here. And the diver, the estimate of the diver was a bit wobbly at the beginning, going up and down. But then the diver actually went along the path as desired. Now, there was a problem here at the end because we did one mission at night and the diver was very happy. Yeah, I could do it. But guys, I was going bananas. Why were you going bananas? Because it was out in the dark and we could only see the LEDs flashing. He said, this is very bad. I mean, psychologically, it's horrible. You got to do something. So then he said, you should develop these piezoelectric devices on the right and left so that you turn left and right. But we never did that. Any one of you wishes to do that, that would be great. So this is real data, and you have all the filters and the controls and the estimation going on. I'm not going to spend much time with this. Okay. And then after this was done, we got into another beautiful project called CADI. So this one, there really was not much interaction between robots and divers. I mean, the diver was there and the robots were at the surface. What about true interaction underwater? And this is the image that we had in mind when we submitted the proposal. So you are doing some form of survey and, oh, I need to collect some rocks or some tools, and with gestures, you should have one more or more robots working around you, and they should come into your neighborhood, and you could pick up a tool or put some specimens in the basket. That's what prompted this project called CADI. It's again a very fascinating story because there's the question of safety. If you have a robot operating very close to a human, you have to make sure that the robot is not going to harm the human. But in terms of navigation and relative control, it's a very challenging problem. Okay, so this is some of the stuff that we did. Diver and surface vehicle and so on and so forth. And then still along the path of cooperative systems, we completed a project, and this one I will focus on it and I will give you many of the details because we learned so much in the process here. And let me see if I have, I'll explain to you what the situation is. If you want to find out what is under the seabed, and this could be an oil field or mineral reservoirs or gas, whatever, the way it is usually done, you have a large vessel, extremely costly, that carries a very powerful acoustic source. It's called a sparker or a boomer. So boom, and it generates all these waves here, you see? So these waves at the bottom get reflected. Some of them penetrate, they refract, so on and so forth. And then typically you have many, it's not this picture, but you have many cables connected to the ship, and the cables have hydrophones. They are microphones underwater. And then all the data that comes from reflection and refraction gets collected by the microphones, and you give this to a good geologist, and he or she will be able to find out from this data what is underneath the seabed. It's just plainly beautiful. This is very costly. And thus we came up with the idea of replacing the surface ship by 2 robots carrying sources. And instead of having long cables that are called streamers, they can get entangled. You cannot change the geometry. So we decided to propose many vehicles with small streamers, and now they behave as an antenna. You can change the form of the antenna, and in fact, you can go up and down. So we concluded this project in 2018. It has all the ingredients that you would love, you know, in order to study planning, navigation, control. I'll get into this. And this is the very first run that we did with one surface ship with the boomer or sparker, another one Italian, this one is Portuguese, and then you had a bunch of vehicles, and they would then dive and carry these streamers. There are many, many other interesting applications, and I think some of the most exciting ones nowadays have to do with offshore infrastructures for wind and wave energy, and for also for aquaculture, because you are going to end up having these farms. And let's dream a little bit about this. So you need to inspect these farms. So why not think of vehicles that are dormant at the bottom of the ocean? You have to find a way of recharging them. Now and then they wake up and they go around these pillars, they do the surveys, they come back to shore and they transmit the data, and they go down and they sleep again, so on and so forth. In fact, we are preparing a proposal now that is even more crazy than this, because the European Union is now putting a lot of money into what they call morphing vehicles. A morphing vehicle is a vehicle that can be an air vehicle and suddenly it becomes a marine vehicle and an underwater vehicle. It's totally crazy. Can we do that? I don't know. But you see, if you have these infrastructures out there, there's no reason, if you can actually build one of these hybrid air, surface, underwater vehicles, to first go around and inspect the propellers, and then boom, down, and inspect the pillars, and then come back to shore. So that's the dream. We'll see how it goes. So, oh, there's some noise in. So, how do we go about building these machines? I'm going to go through these slides very quickly, because the topic is, it's very simple. But on the other hand, I should give you an idea of the type of systems we need to develop in order to make them operate. So here you see one of our surface vehicles in operation at sea, and one of our underwater vehicles coming from the water column and resurfacing and doing these things there. Okay, so underwater vehicles, there are many, many, many. I mean, you name it. Representative AUVs. There are some that have become extremely famous, such as Hugin from Norway, the Remus from the United States, and many others. We built our own, no, not our own. This was built in a consortium of European partners, Portugal, Denmark, and France. It was called the Marius AUV. We think it was the first European commercial AUV built there. So for you guys that like oceanic engineering, so these vehicles essentially have a very simple hull where you can put all kinds of cylinders, and then use some form of material to cover it up to give it a nice shape. And then you maneuver it, because this vehicle is made to keep flying. You use these surfaces to control the vehicle. So notice that we have two back propellers or thrusters. These are called the bow planes at the bow. We have one stern plane and two stern rudders. So this will allow you to move up and down and move left and right. That was the Marius AUV. It was designed to fly in a very controlled manner above the seabed, no hovering capabilities, and then do a bunch of things. Now, the actuators, of course, were propulsion, no big deal, thrust force. And then the actuator surface, so you do the surface deflection, and you generate the forces and torques required to impart torques. So as you know, it's moving at a certain speed. You have a cut of these foils, and you generate lift. So if you want the vehicle to dive, you could acquire a certain speed, you deflect the surfaces, you generate lift, generate torque about the y-axis, and you start diving. That's how you go. Okay. Oops. It's not kind. Okay. So then later we built our own AUV called Infante, and you see an example here. Okay. The same configuration. And here is an example of the vehicle. It still had an umbilical, very thin. I mean, all the intelligence was on board, but we wanted to find out how things were actually working. So it's a flatfish kind of robot that is specially designed to maneuver and stay horizontal with respect to the seabed and to acquire all these beautiful images. And you'll see it coming from there in a very stabilized manner with the fins or planes. So it's a beautiful machine. Okay. So it's not worth showing this because, yeah, it has propellers on the back that are extremely powerful. So essentially it jumps out of the water. Then there are ROVs, remotely operated vehicles, and these have been quite popular, especially in the oil industry. They are different. So they are essentially designed to maneuver in all directions. This is very important. If you look at this vehicle here, this is what we call an under-actuated vehicle. So when you acquire a certain speed, you can only impart on the 2D plane, you can only impart acceleration on surge. You cannot impart pure acceleration on the lateral axis. So it's called an under-actuated vehicle. Sometimes people call them non-holonomic vehicles, for those of you familiar with the mechanical term. Oops. Okay. These vehicles have thrusters all over the place. I mean, on the horizontal plane, there are usually 4, and you could have 3 more on top, so that you can actually do very fine maneuvers like going forward and backwards, going sideways, rotating, because they are designed to explore the environment. It's not only go with the flow. It's not torpedo anymore. This should be very highly maneuverable. There's another example of a vehicle that was designed in the context of European project. And also, as far as I know, it was the first European underwater shuttle. I'll tell you why. So scientists like to have what they call labs. They are called Ventic Labs that are stationed at the bottom of the ocean. Okay, so you leave them there for an extended period of time. And it's very easy to recover them because you send an acoustic signal, they release a weight, and whoosh, they come back up. The problem is to place them there, which is a very difficult operation if you want to position them on a particular spot. So we wanted to develop an automatic manner of doing this. So we developed this shuttle. It's not seen here, but this guy can connect to a big lab. Then on the vessel, you simply key in the coordinates of the target point, and this guy should be able to go there and deliver and then release the Ventic Lab. So that's a big vehicle. This was tested long ago off the coast of Toulon in France. You see. And I think I have some footage of the vehicle without the Ventic Lab, but still it's a big beast. And the sea was a bit rough. So you test all the systems, then you go in the water, you launch it. You see a little bit, then you lose sight of it. And then there's an artist's rendition of what it should do with the Ventic Lab. So it goes down then, and then when it gets to the bottom with a certain position and certain orientation, and it releases, come back up, and then the Ventic Lab will keep doing its job. In terms of autonomous surface craft, there are very, very interesting vehicles out there. These are examples from a UV lab at the MIT, Stanford University. And this one I don't enjoy particularly because it's equipped with a machine gun. But anyway, it's an example of autonomous surface craft. Okay, all right. So I'll give you a little bit of an example of how we operate our surface vehicle, the Delphi. It's a very simple vehicle. So in some respect, it reminds me, and because it is simple, conceptually, I think that's where the elegance comes from. So it shares some of the characteristics with the vehicles that we have here at IIT Madras. So it has the basic electronics, GPS, then well, in this case, it doesn't have rudders. It only has 2 thrusters, so on and so forth. But, you know. So from theory to practice, final lab tests, and then setting up the RTK structure so that we could measure the position of the vehicle at sea with very good precision. And then we went from one big island to on top of the volcano. This was a map that we had there. So you see the rim of the crater, and then you see the inside. Okay, operations at the seamount. So the vehicle equipped with some units that I'll mention, and then the Delphin vehicle at sea. So at this point, it becomes completely autonomous. So it knows the path that it has to go through, but it's completely on its own. It has to fight the waves, the currents, and go about its life. So tested in the presence of currents and wave action. We were doing a very simple mission, simple going back and forth. That's what we call a lawn mowing maneuver. A precision was better than 1.5 meters. We can do better than that now. And this is what happened. So the vehicle is sitting there. We are uploading the mission, and then we don't interfere with it anymore. So it's a beautiful platform because you can try all algorithms for navigation. In this case, it's very simple because you have GPS. But in terms of control, keeping the vehicle on top of a desired path, it's exciting in the presence of currents and waves. You can do that. And once you become relaxed about this, then you can start looking at the seabed with the acoustic sensors that I mentioned to you. So here is an example. This is real footage. It's not CAD. You see the propellers, and here you see the acoustic sensors that are insonifying the water column and detecting the reflections of the seafloor to build a map of the seafloor. So, incidentally, this is very interesting. This is the vehicle going along. You see the rim of the crater. You see the interior of the crater. And you see this, these are bubbles. The bubbles, they are essentially gas, so they reflect the acoustic waves. It's a good way of finding out where the hydrothermal vents are. And here I'll show you a map. So the beautiful part about this is that you can imagine that this vehicle can be used to do what we call bathymetric surveys near coastal, to find what the terrain looks like in places where the big ships cannot go. Because just having this vehicle, performing this mission, having the acoustic sensors, and then you acquire the data and you build a map. So you see very well the crater of the volcano, the interior. So for example, if you want to inspect an harbor or a region near shore, I mean, you could get into the business of developing these vehicles to do that. They are cheap to manufacture, and they are very helpful for scientists, for commercial authorities, commercial companies, and the authorities, of course. These are examples of our vehicle operating in the Azores and operating in Portugal, in a specific area near Lisbon, but I'll get into this. Okay. And this is the vehicle that we designed, the Medusa. We can build it a bit cheap now, not so cheap, but cheaper now. Maybe, I mean, with all the paraphernalia, it's probably around $25,000, $25,000, but we can bring the price down. But look, I mean, why is this thing expensive? Because we have to incorporate acoustic sensors from the best are from a company in Germany called Robotics, and one of these units itself is about $7,000. So that's why the price is so high. So other than that, you can buy one you can build one very cheap. Okay. Okay. Beautiful. So the business of cooperative multiple vehicles, you need to have more than one. All right, so this is our vehicle here. They are very easy to operate. So at this point, we have 3 of these, and we wish to build more. Transportation is easy. You deploy them, and then you operate them. And this video I already showed to you. There's something also very interesting that we did with NIO, National Institute of Oceanography in Goa in India, that we developed this vertical profiler. So this was some form of collaboration that led to the development of a very interesting AUV called Maya. This was long ago, and it was operated in Goa. And there is Maya, and this is before 2000, so long ago. It was a beautiful design. Then it was commercialized. I don't remember the name of the company. So you have all the ingredients, the torpedo shape and all that stuff. And then they went along, and this they developed on their own, the autonomous vertical profile. The autonomous vertical profile is a very interesting machine because this was motivated by the fact that along the coast of Goa, and in fact along the coast of India, you like to find out how some parameters in the water column are evolving along the day or along, in the period of months. So you like to have this machine to go up and down in a controlled manner. Of course, you could have a machine that boom, goes down and then goes up and goes down, but you want to control it to do it in a controlled manner, because depending on the type of data that you acquire, you may decide to slow down or speed up. Hey, there's something interesting here. Let me slow down. So they developed this autonomous vertical profiler, which I think was also commercialized. There you go. Let me skip this one. And then we had the visitor in Goa of a guy from Denmark, very interesting guy. And he had a brilliant idea that has not yet materialized. So he looked at the vertical profilers developed in Goa and said, well, this excites me because I can think of some useful stuff to do with them. So this guy had found a very interesting paper, I think it was on Nature, about the behavior of the horse crab, I don't know. There's some form of larva. I think it's all scrab, something like that. So anyway, the larvae are spawned out in the middle of the ocean, and then somehow they have to get to the estuary of the river by using the currents. So how in the heck did they do that? Because they cannot fight against currents. So people find out, and this is fascinating, that they stay at the bottom, and they somehow have a way of sensing when the current is in the direction of the place where you wish to go. Then vroom, they rush to the surface and they go. And when the current starts deviating, they go down again, up and down and up and down. This is very interesting. And then, oops, another guy here. Because he had published a paper, a very interesting paper, just for one of these things going up and down. I'll show you. Here you go. It thought in the following manner. If I am in a region that these are called the intertidal areas, so out there near the coast, and the current moves along, turns 360 degrees in 12 hours, I believe. So if I want to use a robot to go to one side here, another side there, and take measurements, I should take advantage of the current. So probably I should start by benefiting from the current to go to that spot. And then when the current is not useful, I come down and I protect myself. Then I go up again and wait for the current to turn into that direction. And by doing this, you keep visiting the sites you are interested in using very little energy. So that's the idea he had for the vertical profiler. Why don't we do this with the vertical profilers? And this was never done. So it's another good idea to explore. And then we had the idea of using more than one, but never materialized. So it was the idea of having more than one. Okay, so I already mentioned to you a bunch of what I consider to be very exciting missions at sea and why these robots are necessary. We know how, more or less, how they are organized. And now we should learn a little bit about navigation, guidance, and control without getting into many details yet. Okay. So navigation, again, in robotics is the act of finding out where you are. So from old times, where am I? Where am I going? That was called navigation. And again, remember Nautil and the demo, the pilot of the submersible. Oops, something happened here. Okay. Okay. Now, if you read the book by Jules Verne, he already had embedded in there the basic principles of guidance and control. What are we talking about here? So he knew where he wanted to go. Using navigation, he knew where he was. And then, oh, now I have to guide and control my system to go in the direction I actually wish to go. Okay. So how was navigation done in the old times? Well, you know this. I mean, the first thing you do is you estimate the speed with respect to the water. Essentially, you have a rope with knots that you launch from the bow of the vehicle. Then you have another sailor at the stern, and the sailor will count the number of knots per unit of time. That's where the word came from, knots. So you estimated roughly the velocity or the speed, the longitudinal speed with respect to the water. So now you know that. And then the other thing you did was to have time and the speed, and you need a direction through a compass. So now, if you assume that the flow with respect to the boat is aligned along the main axis, and the current is not very strong. So now, if you know the intensity of the velocity, you know the direction of velocity, you know the velocity vector. So you know where you start integrating, and you compute your position. That's the basic idea of navigation. It's different from aerospace, where you start with accelerations, not with velocity, because here you can measure the velocity with respect to the water. But up in space, you cannot measure the velocity with respect to the vacuum. God knows what that thing is. Okay, so this way of doing navigation, of course, it's okay. It's called dead reckoning. Don't ask me what this means. It's called dead reckoning, and it led to complete disasters. Because you know, if you don't know the currents, because you are measuring the velocity with respect to the fluid, the inertial velocity is the sum of this one with the velocity of the current. So you are heading maybe in that direction, but still you are going what we call flying crab and going in the other direction. So many ships were lost because of this, because people were not aware of the There's a famous ship, a famous example of an expedition, Spanish, that was led by a guy with a strange name, Cabeza de Vaca, means house face. So he started off Cuba and wanted to go to Mexico. No, he started off Cuba and wanted to go off to Mexico. And he was using that reckoning, but the current was so strong that he ended up in Florida. And then he had to go by foot, and of course they were attacked by all kinds of people. Okay, so modern navigation. So instead of counting the knots, use what we call the Doppler device, you know, the Doppler effect, right? So the Doppler device can give you the velocity with respect to the water or with respect to the sea bottom. If you shoot very strongly, it will touch the sea bottom, and then you measure the velocity with respect to the sea bottom. If you shoot in a nice manner, you don't go very deep, then you are the waves are reflected from off the particles suspended in the water. And still, this is a very old Doppler. Now they are extremely small and cute. And then there's an attitude and heading reference unit. Sometimes people call these inertial units, but that's not true. And these you can buy very, very small now with well, on your cell phone, you have this kind of stuff. So no problem. The acoustic modems, Doppler, you measure the 3 components of the velocity vector. Okay. They emit 4 beams, and then you can measure these components. The problem is you have to correct for the drift. Okay. So now, when you are underwater, so here is where the problem becomes difficult. You are underwater, you are measuring the velocity with the Doppler plus the heading unit. You start propagating and you are going to drift because of currents. How can you correct? That's the difficult part. Well, you could resurface and take a GPS reading. You don't want to do that all the time. So another way is to install what we call transponders on the seabed. You know exactly what they are. And you excite them and measure the ranges and do some computations, and you find out where you are with respect to that baseline. Now, imagine that each time you want to do this, you have to deploy the transponders and calibrate them. It's a pain in the neck, so you don't want to do that. So there are other ways that we have to think about. So bear in mind that navigation is the act of finding out where you are, and also at what velocity do you go. So navigation is the act of finding 12 variables: position of the center of mass, velocity of the center of mass, orientation, 3 angles, 3 Euler angles, and 3 rotational speeds. So 12 variables. That's what the navigation system gives you, okay? So I'll get into this a little bit. So when you have a rigid body, like a submarine, you have the position of the center of mass, the velocity at which it is going, and then the rotational speed, and then, of course, the orientation. You have to measure this. There are many ways of correcting for the drift, and I'm not going to get into it. I mean, it involves the use of acoustic systems. Some of them are complex, the other ones are not so complex, but we'll leave this for a later time. Now, there's a very nice way of doing this that is extremely cheap, and we use this a lot. If you have an underwater vehicle and you need to find out where it is, why not simply do this? You have a surface vehicle at the top that is capable of computing the distance to the underwater vehicle. This is trivial. It's using a ranging device. This is very cheap. And then by accumulating information about the ranges and doing some inspired maneuvers, you'll be able to find out where the underwater vehicle is. It's called a single beacon navigation or single beacon positioning, which is a very exciting area. So you have all kinds of cooperative navigation, many vehicles, but let's not get into this. Okay, let's skip this. So what is a navigation system? And I'll get a little bit into this. You have a bunch of sensors. You have the computer and navigation algorithms. And you should be able, after some processing, and you should be able to compute the 12 variables: position, velocity, orientation, and rotational velocity. That's what you wish to do. So when people tell you, oh, my vehicle has an inertial unit that gives me this, well, it's not exactly an inertial unit, but it's a unit that should give you all these variables. If you are interested in maneuvering in the horizontal and vertical, of course. All right. Guidance and control is different. So navigation tells you where you are and in which direction you are going and at what speed. So control is the act of, if you are moving in with a certain orientation, with certain heading angle, and you want to change the heading, let's bring in a control system to do that. Okay, so you have a computer control algorithm, you have a vehicle heading sensor, you have the desired heading, you are heading north and say, now start heading east. So you measure the heading, compute the difference, And the algorithm should be able to maneuver the stern rudder or the two propellers in order to steer east. That's it. That's a very simple example of a control system. There are other control systems that you have to bear in mind. You control the speed, but the same applies to a boat or a ship at the surface. Control the orientation. If you start diving, you control the depth, the altitude above the seabed, and there are other kinds of control systems. So the big question is, how do you design controllers to make the vehicles do what you want them to do? So there are many schools of thought here. There's what we call the model-based design, which is my favorite because I have sufficient age not to learn any other methods. And there are, how do you call that? Data what? Data-driven control system using machine learning and AI and all those kinds of things. Okay, so I think there's place for the two. That is the nice thing. So how do we do control systems design using the classical approach? That's what you do here for ships. You have to find a model. So this is an example of the tests that we did in the circulating water tunnel in Berlin. For that vehicle, the Sirene, we had a mock-up version, I mean, a prototype here, not scale-up version. And then we had the water circulating, and then we had the vehicle facing the water at different angles, and then we have force and source torque sensors, and then you calibrate the model. There you go. And then based on this, you do the design. So controls, we have talked about this. What's this stuff of guidance? You hear the word guidance. It's very important to understand what guidance means. So if you go to the book Alice in Wonderland, would you tell me, please, which way I have to go? Well, depends a good deal on where you wish to go, said the cat. Suppose you have a path that is a straight line, and your vehicle is somewhere out there. So in which way should you go? It depends on where you wish to go. And what you wish to do is for the center of mass of the vehicle to smoothly converge to the path and then fly along this path. This is the act of selecting in which way to point in order to execute a certain maneuver. It's called guidance. This is what we call guidance. So guidance should not be confused with controls. So again, I repeat, you have a path. You want to control, suppose you go at a fixed speed, you wish to control your heading so that you reach the path and move along it. It's called guidance. Where does the control come into play? The moment you decide which heading to take, then you activate the control system and tell the system, hey, I want a vehicle to go to the particular heading that I'm commanding. So that's the structure of the cascade of guidance and control. So I'm going to give you a very simple method of guidance that will allow you to design the simplest path following controller you may have in mind. So what you do is the following. You have the vehicle and you have the path, and you compute the closest point. Oops. So the vehicle goes with a certain heading. You compute the closest point on the path. So it's a very simple operation. I mean, you are anywhere at sea, you know where you are. You know the path that you wish to follow. You compute the closest point, okay? And then you introduce this mysterious thing called visibility distance, which says the following. Okay, I'm not going to be nervous because I'm here and the closest point is out there. I'm not going to react instinctively. I'm going to relax a little bit. And instead of starting pointing the vehicle in this direction, I give it some visibility distance. This is the number that you choose. You have to choose this number. And then you point the heading in that direction. This is called line of sight. Okay. It's marvelous because if you keep doing this, the vehicle will actually converge to the path and follow the path very nicely. I think this was inspired by the animal kingdom. I read that some animals do actually this when you have the predator chasing the prey. If the predator is a bit stupid, doesn't have many neurons, it's going to react very instinctively. Oh my God, the prey is right there, so let me move sideways. It's going to generate a lot of lateral acceleration, gets tired very easily, and not very much success. If the predator is intelligent, it can sort of predict the path of the prey. So now I'll wait for you. It gives this visibility distance and gives it small, smooth approach to the prey, which is very interesting. Okay, so that's a very basic guidance system, all right? So remember, when you have a vehicle like this, you have all of these blocks installed. You have the vehicle, you have the, for example, a path to be followed. The vehicle tells you where you actually are through the navigation system. The navigation system tells you where you are, you know where the path to be followed. You activate the guidance system, and the guidance system will tell you which heading to go through. And this will activate the control system that is going to activate the vehicle. So in order to make one of these vehicles perform well at sea, and this applies to a surface ship as well, you have to have at least these vehicles, these systems working in real time. So navigation, guidance, and control, NGC, very important word. So it's very important. So when you build one of these vehicles, you start with the hull and the energy. So first, the basic stuff, okay? Then you put on top the propulsion and the actuators to make the vehicle move from one place to the other. Now you are a little bit more relaxed. Now you have the vehicle and you have a way of making it maneuver from one place to another. Okay, now you need to find out where the vehicle is, navigation. Once you do this, then you can install all the systems for guidance and controls. And now you are in very good shape because you have a platform that can move around, that can find out where it is, and you know how to maneuver so that you actually follow or do whatever you wish to do. Now you relax even more and you say, now I want to communicate with the surface ship or shore. You have the communications. And now you are really in good shape, and oh, now I want to do some more sophisticated things. I want to look to know what the environment looks like or feels like. So you have all these mission sensors that can measure temperature, salinity, or more complex things like vision systems, for example. And now comes something that many people don't pay attention to, and then they suffer in the long run. Look, when you have a complex vehicle like this, I'm not saying it's too complicated, but it's complex. How do you make this operate like a nice orchestra? You need to have a dialogue among all of these systems. So this is, oh, this is funny. Oh no, I want to build up the suspense. Okay, so in the case of our vehicle, these were some of the mission sensors. Then you can start looking around. And now you have something very, very important that we call the mission programming and mission control. Because when you develop one of these vehicles and it's going to be used by a scientific or commercial operator, you cannot come on board with 12 engineers. It's impossible. You have to make it in such a way that it's very easy to program. So you need the mission control. That's the central system that talks to all of these systems and talks with the operator. So for example, you could start by designing some simple mission. Like in this case, I want to do a lawn mowing maneuver with a certain distance between legs of the journey. And then you have to have automatic code generation and real-time vehicle system control, okay? So that's the top, that's the mission control. I understand it's probably a bit difficult for some people from ocean engineering. I mean, I don't know much about ocean engineering, so I cannot expect some of you to know about computer systems. But so the question is, how do we bridge this gap? You have developed all these beautiful systems for your vehicles. Oh man, now I have to implement it on a computer that runs in real time. How the heck am I going to do this? You need someone to help you. I mean, you have to be inserted in a group where there's people dedicated to doing this. I mean, maybe you can lead it to the stage where you simulate things in MATLAB, and then maybe you can program in C++ or Python, but then you have to get a hold of someone that, for example, knows ROS to implement it, and it's not terribly difficult. But please don't despair if you have to implement this. You just have to find the help of someone and work in a group, work in partnership. It's very, very important. So this mission control becomes very important. Unfortunately, it's not something that you can publish because it's not terribly glamorous, you see. Some people don't go in this direction because they say, I cannot get many publications out of this. Yeah, but it's important. It's very, very important. So there's the mission control. And that's where you bring all the paraphernalia and the control systems and stuff like that. Okay. So now, I don't know if you wish to stop for 10 minutes or so. Should I? Or 5 minutes, because I need to change slides here. Okay, 5 minutes. All right. So I have to go to the other stuff. Okay, 5 minutes.
Even if switch off, it doesn't switch. Yeah, if it switches on, switch off, even if it's called. I think. Why is not going to last that? Yeah, tomorrow I will arrange a coffee.
You are trying to seduce the students. Camera? Eh?
For me too.
Yeah, for you too.
It's a bit cold here.
Yeah.
Last it is a bit cold. For you,
I'm not feeling it
yeah,
now.
because you're from Europe. Not from here.
Oh yeah, yeah, yeah. So I know that Pramod is there now somewhere. Hi Pramod. No, he cannot speak.
Hi, António.
It's red. I don't know.
Hello, António.
Okay, so welcome back. So I would like to finish this introduction today, but I still have so much to show, and also the results of a very recent project. So I'll move a little fast before, and then tomorrow I'll get into the real business. So again, I stress where the challenges are, the pressure, lack of optical visibility, navigation is very hard. And then something I have not mentioned before, when you wish to communicate with these vehicles, with the best modems in the world, probably you can reach around 32 kilobit per second. I mean, it's a nightmare. What can you do with 32 kilobit per second? So you cannot do control from on board the ship. You have to have all the intelligence on board and now and then communicate with the vehicle. That's what you can do. It's the best you can do, right? So I already mentioned this to you, so I'm going to skip. That's the rationale that got me introduced into cooperative stuff. And then this was around 2000, and it was dormant for a long period of time. But around 2010, a new era came up. Why? Because we start having access to small embedded processors. The sensors were miniaturized, the price came down, it was amazing. New acoustic and optical modems, also very interesting. Miniaturized positioning systems, and because the stars were aligned and suddenly we had theoretical developments along the lines of cooperative motion planning, navigation, and control that I will mention a little bit. Okay. I like to show this figure because it's a fantastic example of how things develop. This is a device manufactured by some company in Germany. And it has everything in here. So it has an acoustic communication system, so you know how it works. So it has piezoelectric effect, and it starts vibrating and induces pressure waves. So, okay, you can send data to and receive data. You can also send an acoustic signal and wait for the reply. And when the reply comes, it's going to arrive at these 4 receivers with different phase, or let's say, without being too rigorous, different times. And by using some contrived algorithms, you'll be able to find the incoming direction. So if you have something that pings and you can compute the time at which the host, not the host, the guy that received the ping replies, you have a measure of the distance. If you can also measure where it came from, then suddenly you have the relative position vector. So this means that you are underwater, you can ping your neighbor, and you can find what's the relative position with respect to your neighbor. This was a game changer, okay? This was truly a game changer. All right. So let me revisit the morph vehicle because that's where we use all these paraphernalia. I already mentioned to you, so I'm not going to repeat myself. So here is the scenario. How do you make this operate? So you have a surface vehicle at the top that knows where it is. You have another one that is very good at guidance, navigation, and control with respect to that one. Then this one can also navigate very well with respect to that one, and it carries a sophisticated sensor. And then all of these must fly information so that the ones at the bottom examine the seabed, and when this guy detects there's a onset of the wall, then they maneuver differently. So in order to make this operate, we need for the vehicles to communicate with each other. So you need acoustic communication. You need for the vehicles to find their relative positions with respect to each other. So ultra short baseline, the thing I showed to you. And then you need the controls, of course. Okay. So here is an example. We had 9 partners and 5 vehicle providers. So this top one was our vehicle. This one was our vehicle, Spanish vehicle, German vehicle, French vehicle, and another Spanish vehicle. So very, very interesting. So that was the beginning of a nice story. So the idea was to go near a wall and do a map. That's what we call a mosaic of that wall. And these are the vehicles that we used. So the first trials, we did something that was relatively simple conceptually. So this is the site in the Azores. It's a beautiful place. So remember, we have 5 vehicles in the water. The top one knows what it is doing. The other one should automatically find out how to maneuver in order to stay information. So these are some islands out there in the middle of the ocean. So that's the place we selected because there's something at sea with a nice wall to be inspected. And then the boats, support boats. This had some sound to go with it, but I guess it's gone anyway. All right. So you have the vehicles. So the first thing you do is you program the mission for the top vehicle. So these are the examples of vehicles that we used. So again, from Spain, Germany, France, and Portugal. So 3 of our vehicles from Portugal. And that's the operation center, the mission control. So the mission was to perform a horizontal survey where the top one dictates the rules. It's out there, and the others have to learn on the fly how to keep all these configuration and acquire images from the seabed. That's a snapshot of the vehicles underwater, but you'll see something more interesting because you'll actually see the vehicles in operation. So mission started. The vehicles are diving. So that one at the front knows exactly where it is going. The boat goes, and now the mission starts. So remember, these 2 on the side are very close to the seabed acquiring images into the arc. For example, when this guy decides to go into the arc, the other ones should learn that it's going into the arc and should maneuver accordingly. You still see some umbilicals because we were at the beginning of these tests and they are doing nothing useful, just transmitting information back to shore. Here you see the vehicles in operation. So you see each vehicle has all these thrusters here, vertical thruster, horizontal thrusters. That device I showed to you, it's right there, the ultra-short baseline. And they are checking the relative positions so that they move information. So there's one vehicle on top. There's this vehicle here. There's one on the right, which is the German one. There's one on the right, left that is the Spanish one, and then there are the ones on top, and that's the German vehicle. Now, when you see this in video, say, okay, big deal. Yeah, but it's true. I mean, but to arrive here, we had a lot of work and a lot of bad moments where essentially we didn't know what the vehicles were doing. But when everything falls into place, it's beautiful to see the operation of the concerted operation. Okay. To show you what kind of sensors these vehicles may be equipped with, I'll show you this video, a particular spot. So these are tests now in Spain, in a place called Girona. 132, 132, I can barely see the numbers. Yeah, that's when you will start diving. Okay, and because we have to follow the wall, you have to develop the capability of each one of the vehicles measuring the distance with respect to the wall and keep that distance. And you will see that in operation here, I hope. Yeah. This is a beautiful example of what we call mosaicing, taking video images and then collating them so that you understand what's there along the walls. There you go. One of the vehicles is going to fly very close to the wall. It will remain there. This is not the most exciting part. Let me see. Here you go. What you see here is it's a beautiful sensor. So it's a multi-beam. So a multi-beam essentially allows you to do a cut of the ocean floor. You send this acoustic wave, and then you have ears that scan very quickly this big sector. So boom, you do a cut. But then the Spanish friends mounted it on a gimbal, so they were able to move back and forth. So what you see here as the vehicle moves, it can see what comes ahead in order to make decisions. And it's beautiful because it's all done acoustically. See, it can detect the wall. It can deviate from the wall. It's a beautiful sensor. So it's an example of the type of more sophisticated sensors that you can have on board. And then there's no point in showing another video of this. Okay. So the seagoing machines I already mentioned to you, the vehicles. I don't know if any of you would ever be interested in building one. It's not very complex because you just need the hulls, you need the propulsion, then you need the Wi-Fi antenna, you need a GPS, you need a vector nav, is what people call an inertial unit, which is not an inertial unit, adapt cell, batteries, and the sonar, so on and so forth. And you can put this together in a very cheap manner, and that's what you get there. Okay. Transportation deployment, and then I'm not going to spend too much time with this because it's mostly for people that work with electronics engineering or electrical engineering, computer science. So it's built around the ROS, Robot Operating System. Mission Control Console, to give you an example of how we program these babies. So essentially you have a map of the area, and then you can do simple things like for one vehicle, you click waypoints. I want you to go through these waypoints with a certain speed. I want you to activate these sensors. And then you have access to all the data here on the fly, if you have. So this is how you program. For example, if you want to program lawn mowing maneuvers, you select the type of maneuver, the tilt of it, the distance between legs of the journey, so on and so forth. And then everything is generated automatically. Okay. There's a very interesting phase before you go to sea. You have to make almost sure that everything will work to perfection. So you do what we call software in the loop and hardware in the loop. What is this? So suppose you have a ship and you develop a very fancy system for this ship, for controls and stuff like that. And you are going to implement it on a target computer. And you want to test this thing before putting the ship in the water. So what you do is you run a simulation of your ship, but the code, and you interface it with the code that implements the algorithms, and the code runs on the target computer. So that if you make a mistake in the implementation, you'll be able to detect it. That's called hardware in the loop simulation. And it's very, very important. I mean, we even simulate the acoustic channel, how the messages bounce back and forth. This is an extremely important aspect to do the hardware in the loop simulation. And then we have the test facilities near Lisbon, where we wish to carry out the first tests there, and then we can go in the river. So that's one project. The other project that was very exciting is the WIMAS project I already described to you, where you have a boat carrying the boomer or the Sparc, and then this is the classical approach, where you have this ship carrying this. You know, sometimes these things called the streamers can reach 10 kilometers. And they are pulled by the ship. They can get entangled. Another thing that I was not aware of, this sounds weird, but especially in tropical waters, these things are so long that the clams get attached to it. So now and then they have to send a man on a boat and clean these things during operation, which is it's a headache. So what we did was to replace that. See an operation with the streamers was to replace these with autonomous surface ships and then underwater as well. These systems take hours to deploy and recover, and they are very expensive. It could cost about $500,000 per kilometer square. But this is the type of imaging that you get. I mean, when you perform these missions and you get some images that don't tell you much, but if you get together with a good company, and this is what we did with a company in Portugal, and this image that I'm going to show you keeps fascinating me. So after acquiring the data, this company does a rendering of what kind of structures are underneath the seabed. It could go down to 600, 700 meters. So essentially you are doing cuts under the seabed, and based on the data that you acquired, you see all the geological structures. It's absolutely fascinating, yeah? So that's what you see there. So in order to do this, we developed the concept I showed to you with the vehicles and the short streamers. There you go. And so we have the WeMust concept, 241, 2. So small, 241 should be around here. So this was the WeMust concept, to have a bunch of vehicles underwater pulling the small streamers, but now you can even adapt the configuration of this antenna to acquire the data. So that was our proposal. It was accepted. It was a beautiful project that ran for approximately 4 years. Okay. So I'm going to skip this. That's the WeMust. Okay. Of course, we had to start from scratch. Now, if you ask the question, but what are these streamers? Really, they are very simple. They are these flexible pipes made of plastic. You put all the microphones inside, you fill this with oil, and that's it. These are the streamers. And these are the first tests that we did. Here, all we wanted to do was to run 2 vehicles in a cooperative manner, pulling these streamers. And you see here, it's sped up. You see the 2 vehicles nicely, and they are pulling the streamers. I don't know if you can see that. So that's the streamers being pulled. But then, of course, we have to do this with 4 vehicles, okay? So now, in order to do this, we had to transform that surface vehicle, the Delphin, to be able to generate the sound. And this is done doing what is called, I don't know why the pointer is taking a walk there, what we call a Sparker. A Sparker is a very interesting unit because it has a bunch of electrodes. You generate very high voltage. So boom, the water evaporates. And when it condenses again, it generates the sound. That's the Sparker. Okay, so that's what we used. Oh, okay, there we go. So that's the Spark. That's the real thing. We had another vehicle from Italy called Ulisse, also with a Sparker. I already showed you this video. So what theory was required to do all this stuff? And again, we benefited from the fast-paced developments on a number of things that I mentioned here: motion planning, navigation control, and other things that I will talk about, and that are excellent topics of research. And again, I would like to remind you that we are talking about 3 blocks: mission plan or motion planning, navigation, and control. Luckily, we have been doing this for quite some time for aerial vehicles. And this is a book that we published together with people at the Naval School in the United States, University of Illinois. But we did exactly the same things for air vehicles. So we knew a little bit before coming here. Now, so remember, you have to talk about cooperative navigation, motion control, and motion planning. This is so why do you need this? Because you need a formation of vehicles. So here is the scoop. You have 2 vehicles with the boomers, boom, 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 boom. Now you have a vehicle here that gives a little help, and then you have 4 vehicles underwater, you the streamers, and you have to make sure that these cooperate and they evolve in a formation. It's not easy to do it because you may select one of them as the leaders, but still you have to tell these guys where the leader is. They have to react, to keep shoulder to shoulder, to keep a certain distance from the leader, so on and so forth. So it's a beautiful orchestra underwater when you do this, because you have acoustics, you have navigation, you have guidance, you have controls. So I don't want to get too much into the details of this. It's just to motivate the fact that we truly know need some good theoretical knowledge of cooperative navigation, control, and motion planning. So here are the basic building blocks, the two acoustic sources, and then the rest of the vehicles. So I'm going to skip this, and I'm going to show you the videos. So how is this implemented? You have the vehicle fleet, and then you zoom in on each specific vehicle. Ultimately, all that you need to tell each vehicle is at which speed it should go, what heading, and what depth. And this decision is made by having this vehicle talk to all of the other vehicles and executing what we call a cooperative motion control primitive. A primitive is a basic action that should be executed by these vehicles. So we have many vehicle primitives, but I want to get to the point where I show you the video, because I want to show you something more interesting. This one is interesting because you'll see here the Sparkers, the famous Sparkers. I believe it's here. You see the power, and it's huge there. You just generate those sparks. Okay. And here you'll see the final mission at sea. So minute 1:33. 32. Oh dear. Should be around here. Yeah. This is when we went to sea with all the fleet. So and what we had to do is to excite the seabed and going again on a lawn mowing kind of maneuver. So it was a large international group of people. We were there at sea. You see the streamers being pulled or towed by some of these vehicles. And this is real data now, where 1, 2, 3, 4, 5, 6 vehicles are going on this horse track and acquiring data. This is seen from the top with the quadrotor. And this is the kind of data that we get, and then it can be processed to give you all the beautiful interpretation that I showed to you. Now, there's an interesting spin-off, because at the end of the project, we had a big French company, and they said, oh, this is super, but this is way into the future, even though they are doing something that I consider totally crazy. They are investing a lot of money. And so you see, you start with a classical approach, boat and the streamers being pulled. We did something different. We cut the connection between the streamers and the boat. We replaced the boat by surface robots, and we have small robots pulling small streamers. They want to have one vehicle per hydrophone. So this means that in a survey, they wish to operate more than 200 vehicles. I find this completely nuts, but they have invested a lot of money in it. I don't know what's going to happen. But they said, you know, there's room for good business if you want to do this in shallow water, because the big ships cannot go there. So can you develop a miniaturized system where instead of having this, you have a condensed way of doing them? So we transformed our vehicle that has the Sparker, and then you don't see, but the streamers, when this vehicle flies, they are here, there, and there. So with this simple vehicle, we carried out the first commercial mission for the French company of electrical company of France, because they have a nuclear power station there, and they want to expand, and they wanted to know if the foundations would be good enough, secure. So we did the work for them with this crazy machine, and it was very successful. So we are trying to come up with a spin-off now. As you can imagine, it's not easy to control this under the influence of currents and stuff, because there's a huge drag, especially when you rotate. So, but it's an interesting contraption. And then there are other crazy ideas to expand this, including magnetometers and stuff, but we'll see. I wanted to give you, before we finish with this introduction, with examples of more crazy projects. We are going to submit, so I already mentioned one to you, the morphing robots. This one is equally crazy, and we are going to submit it. It's the exploration of caves underwater. It's very important because of the scarcity of water, at least in Europe, and many of the reservoirs are underwater, and people have no idea of the extent of these reservoirs. Okay, you can dig a hole. Oh man, no, I don't know what to. So why not send robots and map these caves so that you can have a feeling as to what the extent of these reservoirs is? As you can imagine, this is not easy at all, because how are we going to do navigation? The robot could get lost there. So it's a beautiful project. I mean, I don't know if it is approved, we'll have to sweat a lot. And here are some examples of we will be penetrating using an umbilical and then coming back without an umbilical, but we'll see how it goes. This one is not terribly important, and I'll mention this one in another presentation. Okay, the most recent project that we started, and this is going to be very, very difficult, is the Ramones, which is radioactivity monitoring in ocean ecosystems. So what's the scoop here? So there are man-made and natural radioactivity resources in the ocean, and we should be able to map them. Not many people have done this, not with robots. They are an important proxy for geological dynamics, for earthquakes, for example, strong impact on human population, and many, many other things. So can we do it in a radically innovative way? So the idea is again to develop a fleet of robots being able to adapt on the fly, how to move to increase the probability of actually detecting these sources. So we are going to have some radioactivity instrumentation. And for the first time, we are going to operate 2 autonomous underwater gliders that we already have at home, and an autonomous surface wave glider. So the way this will operate is the following. So why do we need all of this? Because you have these sources and you need the gliders to go around and sniff. But you shouldn't go there with an attitude that, okay, I'll scan an area, it will take a month, and eventually I'll find them out. You'll get nowhere because you'll spend a lot of energy and time. You have to be smart. It turns out that most of these sources emit, and this is very important, what is called radon, which is a radioactive gas. So even if you are not very close to the source, it may be that you detect plumes of radon. So imagine one of these gliders going across the plume and then telling the other guy, hey, come here and help me out. That's what we that's what we call adaptive sampling, which is a brand new area, relatively brand new, that is also very, very exciting. So when you want to do something underwater, you want to measure something, you want to find something, instead of going, you know, like a chicken with the head cut off, like running from in a crazy manner, do it in an orderly manner. Use whatever prior knowledge you have, and then have the vehicles acquire data, exchange the data, and based on the data, decide on the fly what is the best course of action. That's adaptive stuff. And you need the top vehicle. Why? Because it helps the other ones navigate, as I mentioned to you. So you'll be operating a wave glider, 2 underwater gliders, and of course, all the radioactive sensors. And again, you'll need all the ingredients of cooperative control, navigation. And now the motion planning cannot be done offline. It's online. It's based on whatever they measured. It's going to be adaptive. Event-driven is another word for that, okay? So it's a bunch of interesting guys it's being coordinated by the university in Athens, Ramones, that's the website, okay? And I would like to finish this introduction with something that we just concluded. I hope I can do this very quickly. and that I find very, very interesting, but I'm a suspect. This is completely different. It's in the area of ocean literacy, which is becoming very, very important. You know, you spend taxpayers' money, and you need to show that whatever you are doing is good and useful for society. What happens is that most people out there don't have any idea what's inside the ocean, what kind of things happen there. So it would be nice to afford these people the capability of looking in the interior of the ocean and finding out what is going on. So what did we do together with our friends in Genova? We came up with the idea, which is the following. Suppose you go into the ocean with a boat and you have an ROV, have a remotely operated vehicle. And this vehicle is capable of moving from side to side. And now you can receive commands and send data to an audience that could be using a smart app. That's what we develop, or in a classroom, or for the general public in an amphitheater or whatever. So this is excellent because it will allow people to actually command the vehicle. They are not giving commands in terms of a rotation of the propellers. No, it's high-level commands. So they are sitting there, and with the finger, they can select the speed forward, the speed sideways, going up and down. And this is what we did. So there's a bunch of applications in robotics, tourism, economy, and stuff like that. But to cut it short, I'm going to show you the video. And then I'll stop with the introduction. So this was a video that was prepared by the guys back home. State-of-the-art robotics with IoT methodologies. So there's this is a very nice example. You see, for this project, we decided to purchase a vehicle that is available off the shelf and that we transform. It's called the Blue ROV. I think the Blue ROV costs less than $5,000. It comes with all the thrusters, everything. It's just a beautiful vehicle. And then we put some stuff on top of that. So the idea was to be able to do data visualization of remote underwater locations. And especially for archaeological sites, it's very interesting. So here is the project proposal. So you see all the communications that are required to do this back and forth. So it was developed by the whole consortium. So then the network stabilization and safe navigation, because there may be failures in the transmission of the messages. So you have to protect the vehicle from bad things to happen. And this is the type of maneuvers that you could invoke: surge, sway, heave, adding rate, maintain heading, maintain date, so on and so forth. These are the high-level commands that can be issued by an operator. Okay, so let's move on. Where does this lead to? Yeah. So the first thing we did was hardware in the simulation, hardware in the loop simulation. So using Gazebo, which is a very good simulator, where we could emulate the motions of the vehicle and the take of video with a camera. So we are using ROS and the Gazebo simulator here. And this can be easily done. Okay. But then what is important, so there were some tests in the pool to assess more or less what the dynamics of the vehicle were in the different degrees of freedom. And then what is nice is that we conducted trials, and the operator was in Italy, and the tests were in the south of Portugal, so very far away. And it went like a charm. It worked very well. So let's see if we can show you this. So this is Italy, in Porto de Viareggio. And then in Portugal, we did our dive on top of a sunken ship the Portuguese Navy that was sunken there. So we went there with the boat, and we did our the first dive. This one is not very interesting because it's the first dive. So let's collect it. And then let's start the business here. That's still the first descent. See, that's the, so now this is sped up. That's why the image is so wobbly. But this is what an operator in Italy was doing. It actually moving is inside the frigate, is inside the boat now, and controlling that vehicle to look at the steering wheel, the cannon up there. It was beautiful to see this thing in operation. I should show you the slow motion because it will be more smoother, but then we don't have time to see this. And then we actually went inside and checked a bunch of things. This opens up a formidable avenue because now you can have the kids actually playing with these gadgets and look at the seabed, looking at the animals, the plants, archaeological studies. I mean, it's beautiful. So that's the remote operation now that you'll see. Our friend Marco Bibuli. So this is in Italy. These are the images that he was receiving. I mean, they are okay. I mean, the channel was quite good. And he was actually giving commands through an app. And this is very good to capture the attention of the population at large, the students, and to attract young students. I think it's great. And then there was also the remote operation in Italy from Portugal, but this was a surface vehicle. So and then again, we were controlling from our lab in the south of Portugal. So this gives you, this is an example of what kinds of things you can do that can attract the attention of good students that are out there. And then from a technological standpoint, it's very challenging to develop these things. Okay, so I'll stop the introduction here. Tomorrow, I will give you some more meaty stuff. So there's someone that asked us if, it's the Royal asked me if if I could answer some questions, and the answer yes. So please go ahead. I don't know if you are hearing me, if you are still out there or not. Do you have any questions to start with? You can always ask me later. So from people that are online, are there any questions? Oh dear. Pramod, are you there?
Yes, I am there, Antonio. It was a wonderful talk.
No,
Thank you very much.
I says, yes, that can be arranged. And he says, yes, sir. So please go ahead. No. I don't know if this is working or not, if they can actually interact with us.
Can you hear me, Antonio?
Huh? Pramod, can you hear me?
I can hear you loud and clear.
Okay, please go ahead.
Yeah, Shivraman is asking a question. So I have a very generic question.
No, I think they can hear me, but I cannot hear them. Huh? What one? Yeah, my volume is muted. Okay. Hello? Yeah, please go ahead with your questions. Yes, the answer is yes, but not for controls. I mean, we are working on a project where we have to recognize certain species that live on the ocean floor. For example, starfish. So if you send a vehicle out there, it should be able to recognize where the starfish are, and then to hover and take very good Okay, and to get the very good images of the starfish, but they have to recognize them. So there's a student that trained a neural network to recognize starfish. It's one of the applications. Of course, the other application is when you want to do maneuvers around offshore infrastructures and you move around very complicated environments, you should also be able to recognize some features, and you can train the vehicles to do that. So for vision, I think there will be very good applications of machine learning and AI. I'm not sure I understand what you mean. Have you put hand on stability of the build system?
I think he's talking about this course will discuss about the stability of the system. Like we have to know what
Yeah. Yes. There will be a chapter on stability of nonlinear systems using Lyapunov stability tools. Is that what you wish to know? I guess. Yes, maybe not tomorrow, the day after tomorrow, it will be there, okay? So if there are any other questions, please go ahead. I don't know.
Can you hear me? Can I ask a question now? Hello?
You are welcome. But if there are any other questions, please go ahead. Otherwise, we'll meet tomorrow. I understand there's an holiday, but we'll have it tomorrow as well, okay? It's only 2 hours and a half. So, questions from the audience?
It's the phase difficulty in navigation due to drifting. So, but as far as I know, inertial units are based on the gravity, Earth's gravity. So, wouldn't it be a constant irrespective of this?
I think you are talking about two distinct things. One of them has to do with the how the way we do navigation for marine vehicles is different from the way we do navigation for spacecraft. Spacecraft, what you are saying is perfectly okay. Use a very good inertial unit that gives you acceleration in all of the axes with very high precision. And because also you know the attitude of the aircraft very well, then you can actually estimate the position of the platform. Now, when you are underwater, it's safer. But remember that when you double integrate accelerations, if you have small errors on the accelerations, boom, it will drift off very quickly. So you have to have very good accelerometers, which you normally don't when you buy these small units that you have available for the vehicles. I mean, they will give you very good information over the short run, but not over the long run. That's why we skip one of the integrators and we measure the velocity using the Doppler. So that's the reason, because we don't want to spend huge amounts of money on extremely good military grade accelerometers. So now, if you are sufficiently close to the sea bottom and use the Doppler to measure the velocity with respect to the sea bottom, you don't have to worry about the currents, because no matter what you are doing, it will give you the inertial velocity. But if you are very far from the seabed, and what you can do is to use the Doppler to give you the velocity with respect to the water, the inertial velocity will be the sum of this velocity plus the velocity of the current that you know. And then you have to find another way of compensating. I don't know if I...
But it's practically
you mentioned RTK, that's when you are at the surface. But I mean underwater, how do you do that?
using measuring acceleration, you mentioned while double integrating, we increase the errors in magnitude. So if we have a very perfectly measurable acceleration system, so it's theoretically possible, but since we can't have that much accuracy, it's practically.
Military submarines do that.
Oh,
but we cannot afford those. I
Oh.
mean, they are terribly expensive. I mean, there's a unit, for example, that is manufactured by the French that has very good accelerometers. It's very impressive. I had it in my hand and I went around my room and it plotted my trajectory. But I think it's around 200,000 euros. I mean, or dollars. My God, we don't want that. Yeah. So we don't want that. No, no, no. Yeah. So any other questions? Otherwise, we can wait until tomorrow. It's getting a bit late, right?
Can you hear me, António? Do you hear me? No.
Okay. Now, you see, there are different kinds of algorithms. I couldn't type much, you can't hear. Oh yeah, Pramod, I'll get back to you. So if you have torpedo-like vehicles, they are under-actuated, right? So essentially what you do, you use them for maneuvers where you keep going. You fly along paths, you follow a certain trajectory, but you don't do things like hovering over something and doing very fine maneuvers. You cannot. You cannot. So with an under-actuated system, you can do things like go to the path and then follow the path. You can do that. But for example, if you want to go, there's so much talk now about docking stations underwater because they have energy on board and they should be able to bring the AUV to recharge. If you have an under-actuated system, how are you going to do that? Because you may align yourself with the mouth of the docking system, but if there is an error, you cannot compensate. So you need an over-actuated system then. Okay, so that's the.
Thank you.
Pramod, what is the future of long-term presence? It's an excellent question. So what Pramod means is so Pramod is at NIO in Goa. What Pramod means is the following. In many of the operations so far, you go into the ocean with a big boat with a crew, and then you launch the vehicles and you are there praying that the vehicles will come back, right? It's very expensive. You should be able to leave the vehicles there for months. People already do that with gliders. But with other kinds of vehicles, we are not doing that yet. So how can we develop vehicles, as I mentioned to you, that could be dormant, recharge themselves, wake up now and then, do their mission, come back. There is a lot of work that must be done along these lines. There are people that already have developed good docking systems using vision and sonar. So I think it's the way to go, but we still have a long way to go. But we need this more and more. Sometimes people call this sustained autonomy at sea. In other words, it's not just going in the ocean for 2 or 3 days, but leave the babies there and trust them. This is the next step. Okay, Pramod?
Thank you. Thank
Yes
you.
or no?
Thank you, António. You put you put light on it very
Okay.
well. Thank you.
Okay, thank you very much. So we'll see each other tomorrow. Hopefully I did not, I said this, make you go away. Please come, I have more important things to tell you about. Okay. All right, so have a nice evening, okay? Thank you. Okay, thank you. So it worked very well. Have you seen the blue roses?
No.
It's cute. Yeah.